Hi, my name is Mohammed Al Musa. I'm one of the biomedical engineers for the team.
Hi, my name is Jerry John. I'm the material science engineer, and we make up the testing team.
Hello, my name is Daniel Ramos Flores, and I'm the mechanical engineer and team lead.
Hi, I'm Hector Flores. I'm the other biomedical engineer, and together Daniel and I make up the design team.
I'm Alec Mills, and I'm one of the system engineers on the team, and I'm also the procurement lead.
I'm Rebecca Gurr, the other systems engineer, and together, Alec and I make up the logistics team.
Altogether, we make up Team 23021, also known as the medical-grade leak-proof spigot for diagnostic reagents and waste. Our sponsor is Roche Tissue Diagnostics, and we are mentored by Pat Caldwell.
For background, the current method for tissue staining at Roche involves dispensing chemicals through a spigot. Now, the spigot is a fixture that regulates the flow of reagents from chemical storage containers, which are known as carboys. Now, one of the ways that the spigot operates in a lab capacity is that the lab technician will take the carboy filled with chemical reagent and use the spigot to dispense it into smaller containers that will be fitted into the tissue staining machine in order to do testing on cancerous tissues. Recently, leaks and other issues have arisen at Roche's laboratories, which are rooted in the faulty spigot connected to the carboy. Roche has found that these issues are caused primarily by mechanical failure and incorrect operation of the spigot. This is a huge issue as a single slip and fall incident caused by leaking from a spigot, such as a slip causing a bone fracture, could lead to Roche losing over $100,000 directly and millions of dollars in OSHA violations and settlements later on.
We have designed a prototype medical-grade spigot which mitigates safety hazards and ensures a secure and safe dispensing of reagents. Moving on, the system block diagram is broken up to show the separation between external entities of the users and medical instruments that interact with the spigot system. The pink correlates to the connector subsystem, green for the valve, and blue for the frame. When the users want to use the spigot, they will turn the handle, which moves the plug up. This allows reagents to flow from the connector into the inlet, out of the nozzle of the frame, into the medical instrument. When they want to stop the flow, users will turn the handle counterclockwise, which moves the plug down, stops the flow of the reagents out of the inlet, and creates a tight seal with the O-rings. Of our 15 requirements for the project, I want to specifically point out 2 that would be discussed in depth. The requirement for spillage requires that the spigot must prevent leakage of reagents when attached to the carboy. The requirement for material compatibility requires the spigot must be constructed out of materials that are compatible with the reagents Roche uses for tissue diagnostics.
Our material selection was based on careful consideration of the chemical properties required for the product. We choose polypropylene and BTFE for its excellent resistance to acidic solutions. The selection of BTFE as the O-ring material is because it has higher tensile strength to handle the compressive force. This ensures that the product will remain durable and functional even when exposed to hazardous chemicals.
A simple soak test can effectively detect surface damage by comparing the data from before and after the test. We can observe any differences and identify any damage that may have occurred on the surface. The results of the simple soak test were necessary to justify the material choice and proceed with the final prototype fabrication. In order to speed up the process, we decided to utilize an incubation chamber for accelerated aging. The incubation chamber exposes our samples to elevated temperatures, which catalyze creep rupture to occur. After 1 month, we collected the sample and analyzed them using scanning electron microscopy. The SEM pictures were essential to detecting any surface damage and ensuring the material can handle reagents. By using this combination of testing methods, we were able to ensure the compatibility and durability of our materials and deliver a high-quality product that meets our needs of our sponsor.
ANSYS was used to analyze the fluid dynamic properties of each rendition of our spigot design. Using the CFX and Fluent toolboxes, we were able to simulate the flow through the spigot, map the backflow patterns, and estimate the exit velocity out of the nozzle, which helped us determine the Reynolds number for the flow type. Here are the results of the analysis. This image here shows the inlet and exit velocity gradients. ANSYS is estimating the exit flow rate to be around 1.36 gallons per minute. This fits within the requirement of 0.75 to 1.5 gallons per minute. After testing, we found that the actual flow rate was around 1 gallon per minute.
To assess for leakage, we adhere to liquid indicator tape to the inlet and outlet areas of the spigot while connected to a carboy filled with water. We let this sit for 1 week. After that 1 week test period, we checked the indicator tape for any instance of leakage. At the end of that testing period, we saw that there was no instance of leakage from the nozzle.
While manufacturing was not in the scope of the project, we wanted to create a durable and simple design that could be taken to production by Roche. To estimate the total cost of manufacturing, we used a design for manufacturing and assembly software, which provided us with an in-depth cost analysis. This diagram shows the estimated manufacturing cost flowdown for injection molded parts with the order size set at 10,000 of our redesigned spigots. The flowdown includes the cost of machine molds, raw materials, labor and tooling, and extra materials required to complete the assembly, such as O-rings. Using the numbers from the DFMA software, the final cost comes out to around $195,000. Compared to the quote obtained to procure 10,000 of the current spigots, the redesigned model saves Roche upwards of $390,000.
We applied the Agile Scrum method for rapid prototyping. Due to the nature of our project, we were able to quickly 3D print and test designs to identify areas of improvement. We would then make multiple design iterations and address any area of concern, fabricate each design, and settle on whichever performed the best. 3D printed models were ideal because of their fast turnaround time and inexpensiveness. This image shows our lineage of spigot prototypes starting with the very first assembly and the final one. Our final prototype will be produced using SLA resin printing and polypropylene. Here's an image of our final prototype. I would like to note that while the actual manufactured model will be injection molded rather than 3D printed, for testing purposes, SLA printing allows us to achieve a prototype that is comparable to injection molding.
Here's a video showing the installation process of the spigot. A lab technician will tighten the connector onto the carboy until the outer shell skips. This click lets the user know that the spigot is securely attached.
So, in summary, our spigot design is going to improve the safety of the spigot, make it easier for lab technicians to use, and allow for Roche to have their own domain for this product and manufacture it at will using injection molding.
We would like to thank our mentor Pat Caldwell, the team sponsors Ian Aguilar, Krista Kramer, and Stephen Lay, as well as Dylan McGuire for his help with 3D printing. We would also like to thank the judges from our presentations for providing constructive feedback and helping with our success.